Yeah, hi everyone. Welcome to this brand new math reading group session. Today we're a bit closer to normal machine learning stuff. We're talking about state space models and especially Mamba and S4 and Hippo. Um, to set your expectations up, of course, this is a math reading group, and you know by now that I don't really discuss results much, although I can totally try and do that if people want. So I'll be mostly giving like the mathematical intuition explanation for these methods, where they come from, and some of the results, especially around Hippo that might are a bit sophisticated. So and then we'll see from there. So to give you a like brief outline, so the first part will be just a like background on classical state space models. They're like yeah, a super old, super classic way approach in science and engineering, and so that's where they come from originally. Then we'll talk about how these guys can used for sequence modeling, so state space SSMs, which has a long line research with the latest one currently being Mamba, that yeah combines some mathematical sophistication and some I guess CUDA black magic is the best way I could think of describing it. And then the fourth, I promise it won't be too long, but like while reading the Mamba paper, I had some honestly Galaxy Brain steak, and I thought it was too funny not to include in this. So, but yeah, hopefully, also, I saw people wishing to discuss more of the details of the paper. So yeah, if people want to discuss, we can try that. Right. So yeah, welcome to Systems Theory 101. Whoops. So as I mentioned, it's like a really classic and broad like framework in engineering. We're trying to model some kind of system that evolves over time. And typically, it's a system which some kind of state that evolves, and it's subject to some kind of input. So that input might be just the outside world, or maybe you have some way of controlling the system. And you, the modeler, you can maybe not observe the whole state. So let's assume that you have some kind of state x of t that would be like the full state of your system. You, like a function would, or a signal would be basically the input, the outside world, and you might only be able to observe some part of the system. So maybe you cannot observe the complete state, but only a finite or some function of it. And so that's sort of this whole general framework. So we assume that you have x of t that evolves over time according to a differential equation, being x dot equal to f of t, x of t, and u of t. So it's a function that depends on both, maybe time, the state, and the input at time t. And then you have the output y of t, also called the response of the system. That's simply another function g of t and x and t. And so it also depends on the state and input at time t. You can, of course, like add noise, add different kind of stuff, but that's the basic one. Um, and if you want, like maybe the canonical example of such a system, let's say X is like the state of all the air molecules inside a room. So that's a very complicated dynamical system. And maybe your input here is the like maybe you can control the heat valve on your heater, or maybe you can control the fan speed if you're trying to get cold. So that's an idea of what an input might be. And then maybe the only thing you can measure, so obviously you cannot measure the state of every single air molecule in the room, but you can measure the temperature with a thermometer. And so that's sort of like, yeah, a good example of input, state, and output. And like a big motivation of this framework is in something called control theory, where typically you have the system, the state dynamics are fixed. You also have some outputs, but like probably not a lot of them, and you can control the input. And the goal of control theory is, if you have a system like this, is to design the control so you can design U of t to maintain maybe some desired temperature. And so, for example, if you have like a thermostat, like some kind of regulation machine that in your house that like tries to maintain the same temperature, that's basically a control system like this. And you can find a whole bunch of things like that. But obviously, sometimes you have the input, and the input is what you cannot control and you're trying to do something else. So yeah, this was like the super generic system of input, output, and state. But obviously we can simplify it a little bit. So a typical simplification is to assume that it's linear in this sense. So assume that x of t or x dot of t is given by some matrix A of t, so it depends on time, times your state plus B, which also depends on time, and times your input. And then your output is going to be another matrix C that also depends on time times your state, and D that also depends on time, that times your input. And note that you might have like B of t, so it depends on time, but you could also have it in some way depend on, let's say, the state. So A could be a function of the state or of the input. It would still be a function of time in the end. And typically we have like some initial condition x of t0 is equal to x0. You can assume it's zero, and we'll be assuming that it is zero in the following. So this is a slightly simpler ODE than the one we had on the previous slide, and it turns out you have something that looks like an explicit solution. It might not be easy to compute, but at least it's something like a solution. So I claim that the solution x of t in continuous time here is simply given by this big function f, so phi of t, t0, and x0. So Mori, that's basically the solution starting from t0 with x0 and after time t. And it's equal to big phi of t, t0 times x0. So this big phi is basically a matrix times a big integral from t0 to t of, again, this big matrix phi of t times the b, so the input, yeah, b of s times u of s. So essentially you're adding the input back into your state over time. And then y of t is simply c of t times this, plus the d of t. And this big thing like phi of t, t0, it's a matrix, and it's the solution of the equation x of t is equal to a of t times x. So basically imagine you only have the state and no input, or the input is equal to zero. That's what it gives you. The solution of that equation gives you this big this matrix or operator phi of phi of t t0. And yeah, obviously depending on what a of t looks like, this can be super hard to compute. So the most straightforward assumption and simplification we can make is simply assume that a, b, and so on does not depend on time, so it's constant. So that gives you a linear time invariant, so also called LTI systems. And yeah, they look like this. And in this case, we can actually explicitly write this phi of tt0. And if you remember from the last time we talked about linear ODEs, right? We have x prime is equal to a times x. And we saw that the solution, the generic solution for that was x is equal to the exponential of the at, so it's the exponential of a matrix times your solution at x0. And so in this case, because we're starting at t0, it's the exponential of a times t minus t0. But otherwise, if you can compute the matrix exponential, you have no problems. And so yeah, we can input that into the equations, and yeah, we basically get the following. You might see that this part here, if you squint a little bit, right, you have some function, you have an integral over s of some function of t minus s times another function of s. And so that's the basic definition of a convolution, and it carries out even though also in the, if we discretize the system to get a discrete time system. And that's one of the main tricks behind at least the basic SSMs, is that because you can express them as a convolution, you can evaluate them, they can be computed efficiently. So, also these are called linear systems or time varying or time invariant because they're linear transforms in some sense. So for example, if I assume that my initial condition x0 is 0, then it turns out that this big integral here, right, this part goes to 0, so you only have an integral of u. This is actually linear in u. So it's a linear transformation. If you assume that you start from zero and u is your like your input sequence or input signal, then y is a linear function of that input signal. So it's a if you think of ML, it's like a basic building block, like convolutions in CNNs. And but also if you assume that the input u is zero, it's also linear in x0. This is more interesting for like control systems where you can control the input. In this case, it's the input that we're trying to model, so it's the first case that we're dealing with. And yeah, so basically these SSMs like S4 and Mamba, they're all linear transformations of sequences. So you map a sequence U to a sequence Y. Notice that I have a slide a bit later on that, but I'm sticking to the more classical notation versus the more ML notation for these systems, but we'll see that. Yeah, we just saw like the continuous time version with ODEs, but ideally, if we want to do ML, we want to discretize them, and it turns out it's easy. So I can just write the following. So instead of the derivative, I just have a recurrence equation: x of t plus 1 is equal to a of t times x of t plus b of t times u of t, and so on. And again, we can also express the generic solution for these with this big matrix phi of t, t. And in this case, we can actually explicitly write what like this solution here because it's simply the product of all these A matrices. So the product of AI from I to T0 between T0 and T minus 1. Yeah, this part here will be important later. And in the LTI case, then we just have a product of matrices, so that just becomes A of T minus T0. So so far so good. Now, you might have seen both in the Mamba papers and pretty much all of the SSM papers, they assume that you're dealing with a continuous time system and that you discretize it. Oh, sorry. So yeah, before talking about discretization, I just have a little word about convolution. So I already mentioned that even in the continuous time, it's basically a convolution. So you can do Fourier transforms to compute it, and the same goes for the discrete time systems. So for example, let's say I have just a simple LTI system with x0 equals 0 and the D matrix also equals 0. Then my output signal y of t is simply this thing here, and again it looks like a convolution. So if I bring in the C matrix back inside, and then just have this thing C times A of t minus S minus 1 times B times U of t, I can write this as just K of t minus S, and lo and behold, this is a convolution, a discrete convolution. And so the main trick here is that at least if you assume that U of t is like one-dimensional, uh, you can compute this very easily simply using a Fourier transform. So because you know that the Fourier transform of a convolution product is the product of the Fourier transform of both terms. And so typically what you do is you do a Fourier transform of both terms, which is n log n, take the product that's linear, and then take a inverse Fourier transform that's n log n. So it's cheaper than doing the full this full operation, which would be more quadratic. Okay, so back to discretization. So a trick is that if you have a continuous time system, we can turn it into a discrete time system. And here we'll assume that we have some sampling or step size delta. And we want to say, okay, x underscore t is simply my continuous function x of t delta. So sampling every delta steps. And then there's a little trick you have to do to like find the new matrices, right? Because they're not quite the same. And there's different ways to do that. So for example, the one mentioned in the Mamba paper is called the zero hold, zero order hold. What this boils on is that you assume that your input signal is constant on the t delta, t plus 1 delta interval. That's the zero order hold. You assume that you can u is represented in some way to the zeroth order, whereas like first order would be linear interpolation. And then if you just integrate these equations, because they're constant, you can actually compute the integrals over from t to t plus delta. and that gives you the again the exponential of a times delta. So that's going to become the new a bar. And then it's a little bit more complicated, but still computable for the b, just this integral times b. And it turns out that if a is invertible, this is, I forgot, this should be b here, so a inverse, so you need a to be invertible, which is not always the case, times a bar minus I times b. And so that's more the full solution, and then c bar and d bar are just the same as before. That's not hard. So that's the zero order hold. But you need A to be invertible. So if it's not invertible, you have other ways. And that's more what they do in the, for example, the S4 paper. Instead of taking like the exact solution in some sense, you discretize or approximate the exponential. So for instance, like recall that the matrix exponential, it's simply a power series. Like you take the power series of the exponential function and swap in the matrix, and that works. And if you take delta small enough, right, all these higher order terms are small enough that you can ignore them, and so you just get the identity that's for the zero term and a times delta for the first order term. And if you like use this approximation, for example, once, let's say x of t plus 1 is about mostly equal to I plus a delta times x of t, that's basically Euler's method. If you recall from last time, right, we take the first order approximation, and so that gives us Euler's method. We can also use another approximation, which is called backwards Euler's method. It's I minus a delta inverse. That's also an approximation. And the trick that they use in the S4 paper is combine the two. So first you do a backward Euler step and then a forward Euler step, or the other way around. It doesn't really matter. And that's a classic technique in system theory called the bilinear transform. And so you now have this new approximation that even though if here not, you see I need to invert a matrix, but you have I minus some kind of matrix. So even though if A is not invertible, um, this matrix will be because you have I minus 8. So it's going to be fine. Maybe not always, but hopefully if you treat the delta enough. So that's how you jump from a discrete time, not sorry, continuous time to discrete time, and we'll see later why like the guys in doing SSMs want to do that. So yeah, the broad idea is given some sequential data, so let's say U0 to UL, we want to compute a new sequence y of t as simply the output of some kind of linear time invariant system of this form. And where here A, B, and C are going to be learnable parameters. So we can learn A, B, and C. And the trick here is to generally assume that this is simply the discretization of a continuous time system, and what you're going to learn is not these A bar, B bar, C bar, you're going to learn these matrices A, B, and C. The reason for that is that it's a bit easier to deal with on the theory side, and also if you want to deal with data that's not sampled regularly or like with different times, like as if you were doing neural ODEs, then you can do that. And it turns out that, especially in the NAMA paper, they mentioned that the being able to treat this delta parameter is very important. Okay, so that's the one remark on notation. So I'm using here the classical systems theory notation with U for the input, X for the state, and Y for the output. But if you look at like the machine learning literature, especially sequence models and RNNs, it's more common to have X for the input sequence, H for the hidden state, and again Y for the output. So this is one important part. Like I think the Mamba paper uses the one on the right. Uh, for consistency, we'll just stick with the normal one. Just checking that there's some chat. Okay, no questions for yet, but yeah, you can unmute to ask questions at any time. Which yeah, if anyone has question now, now might be the time. How to choose a good delta? I mean, there's no perfect right answer. I believe in the Mamba they adapt it, or not they adapt, they choose it or they learn it. So the intuition, at least if you're trying to solve an ODE, you want delta as large as possible so that you don't need to do too much work. Um, but then if you're doing ML like this, it's the different constraint. So there's really no default answer for what's a good delta. But presumably one that's like not too small and not too large to have numerical issues.
Okay, the only benefit of discretization is it makes learning easy, right? Since we kind of learn like a step function, I assume, because it will be fixed for a small delta.
Yeah. Also, typically your data does not come in the form of continuous function. You have like discrete samples. So it's one thing
I
that
see. So it allows you to learn.
like yeah you might have typically I think the SSMs were mostly used for stuff like sound or stuff that explicitly does come from continuous systems. So it makes sense in this case to use the ODEs. And like they've been trying to apply that to language modeling, which is discrete using tricks. But okay, so let's move on. But yeah, heuristics, as is always the case in machine learning. So the yeah, this basic approach of like learning an SSM, it's fine, but it doesn't work that great. At least it has a few issues, mostly related to learning this A matrix. Like the intuition here is that if you let like your optimizer trying to learn a matrix, or if you like take a random initialization, uh, you might have problems if you with the eigenvalues of A. Like let's say A has positive eigenvalues or eigenvalues with positive real parts. That means that some part of your trajectory is going to grow, to explode. And so that if it explodes to infinity, you have a problem with, yeah, numerical stability and numerical precision. And the other way around, if you have like eigenvalues with negative real parts, that means that some part of your state it goes to zero or decays or vanishes, so you lose information. Yeah, in the Mamba paper they take some delta, but yeah, not necessarily principled. So yeah, so that's the sort of main issue with learning A is that you can have some problems with what your orbit does, and so numerical issues and so on. And so the basic idea is to try to keep eigenvalues with the real parts close to zero, so that you don't like explode to infinity and you don't lose too much information, or at least you don't lose information too fast. Another way to like present that is to say we want to preserve the history of past inputs as best as possible. Obviously, we cannot keep like the full history, but maybe we can like try to keep it around for a long time. And I think in the Hippo paper they mention stuff like unitary RNNs, where you have RNNs with the linear map being orthogonal, so all the eigenvalues have modulus one, but that has problems to train itself. So but that's sort of the idea. You want to keep information and not let it grow, explode, or not let it vanish. So the approach they follow in Hippo is okay. Let's try and fix A. So instead of like taking some random A for the state equation, we're going to pick a specific A in such a way that we keep the history of the inputs in some sense. And the way they do that is that okay, suppose I have like at some time t, I want to preserve the previous values of u of my input, uh, maybe up to infinity, maybe only to some threshold, but I want to preserve some of the history. And since u is a continuous function, and in fact a yeah, only continuous, um, you can approximate it using some kind of basis functions. That's basically the whole bread and butter of approximation theory. You have a function that you're trying to approximate as best as possible. And the generic framework is that, let's say I have some measure mu. So if you don't know what a measure is, don't worry. Uh, just assume that I have some kind of inner product f of g. So f and g will be functions with the inner product related to mu, and it's simply an integral of f of x times g of x times this d mu of x. And you can just think of mu here as just a weighting function. So you have an inner product between two functions that is weighted by some other function called mu. And it turns out that depending on the properties of mu, uh, this gives you basically what's called a Hilbert space or an inner product space, and you have a norm because you have a vector space of functions and you have a norm on it defined by this inner product. And what you can do, because it's in a product, you can also ask for orthogonal orthogonal functions. And so the big idea here is we want to take a basis of functions, for example, Fourier or something else, and specifically want polynomials. Why polynomials? Because they're generally easy to deal with, because also they have increasing degrees, so typically it's a nice way to approximate. But unfortunately, if you try to use like the basic monomials, they're typically a terrible basis because they're very much not orthogonal, so it's nasty. So you don't want to use the basic ones. Instead, what you do is you take the monomials and you make an orthonormal basis of them, but it's orthonormal with respect to this inner product that depends on the measure mu. So this is more like linear algebra background, but there's a standard algorithm you can try to take a sequence of functions or vectors and make an orthonormal set of them called the Gram-Schmidt orthonormalization. And here, because we're doing this on paper, it's fine. We can compute those functions explicitly. So in principle, you can always, given some measure mu, try to find a basis of polynomials that is orthogonal with respect to that measure. And so, for example, hopefully this will be clearer. Let's say mu here is the uniform measure on some interval a, b. So I only care about basically what happens between a and b, and the weighting function is the same everywhere inside that interval. If you apply the Gram-Schmidt to that, you get what's called the Legendre polynomials, at least for ab equals to minus 1, 1, and then for any other a and b, you can always rescale, so that's not a problem. And they sort of look like this. So the first term is 1, that's usually the case. Then you have x, then 1 half times 3x squared minus 1, and so on. Another one, notice that here I have a cutoff, right? I only look at what's going on between an interval a and b. You could also take like an exponential decay. Like let's say mu of x is e to the minor x for x greater than 0. Then this gives another set of polynomials called the Laguerre polynomials. And yeah, again, it's just another set of polynomials that lets you approximate functions. And you have a bunch of these, like you have Hermite polynomials. If you take a Gaussian as the measure, you have Chebyshev polynomials and so on. So a lot of like these polynomial bases, you can like frame them as this. So it's sort of a generic way to compute orthonormal polynomials. So the basic idea of Hippo is to use these function bases, these polynomial bases, to approximate the previous states of U. So suppose I'm at U of t, oops, and okay, I have like the full past history of U, and I want to approximate this past of U with respect to some measure, and here the measure depends on t, right? Because it's sliding as I move through time. And so for here I have an example for the Legendre polynomials, but that's it's fully general. So now, because it's a basis of polynomials, I can approximate my signal u of t with that basis. And so I have u of t, which is most like roughly equal to some kind of combination of coefficients ck that depend on time times my polynomial basis that also slides through time. And so now I have my coefficients that depend on time and they actually follow an ODE. So it turns out that they also actually follow an ODE, systems ODE. So C dot is equal to A tilde times C and plus B tilde times U. So for example, if you had the Legendre polynomials, here the measure, it slides through time, right? So it's the uniform measure on t minus delta t. So I only look at delta before, up to delta before t. And then in that case, I can explicitly compute this matrix, and they do that in the Hippo paper, and it's something like this. And again, that general recipe works for any other polynomial basis, but depending on the actual basis, you may have other problems like numerical stability that I think they mentioned in the Hippo paper, either the Hippo or the S4 anyway. So that's the rough idea. You keep an approximation of your previous state with respect to some basis of functions, and because you're sliding through time, you have to keep updating it, but you can do that with an ODE. And so in the end, you just basically use this matrix A, for example, in S4. You keep A as basically the Legendre matrix. So A is now fixed, you don't train it. Or maybe, I think in some papers they mentioned that they initialize it like this and they let it train, and sometimes it's not clear whether they do or not, but anyway. But for S4, for example, they use this matrix A, which I believe is basically the Legendre matrix, but it's not, it's different from the one here, so I'm not sure which one is correct, but anyway. So they do that, but then they use also some clever parameterization tricks to avoid numerical instability. Because one issue with this is that basically you have like very large entries in this matrix, and so if you want to have a very large state, like high dimensional state, you're multiplying by a matrix with very high entries, and so you have like you can blow up, or at least you have loss of precision because you're using float 32. And so they sort of show that using this like clever trick of basically building the state matrix so that you can like preserve the state as much as possible as you go through time. They show that you can actually preserve long-range information, which is their argument is that it's expensive or more expensive to do that with transformers. Um, because it's an SSM, you can use the convolution mode for training, which is the same thing that goes on for RWKV. And then, of course, you can use sequential mode, classical RNN mode for inference, and that's faster. So that was S4 and Hippo. Uh, onto Mamba. So Mamba, they decided, okay, SSMs are cool, but they still aren't quite up to par with transformers. And so they figured, okay, what we need to change here is to make our matrices C, B, and A, they now need to depend on the input. Or at least they need to change on time, and specifically they need to change on the input. So now I have A that depends on U of t, B that depends on U of t, and C that depends on U of t. Again, they use the ODE and then they discretize it with a step delta t that also depends on the state, at least in the formulation. And so now I have uh, linear time varying discrete time system. And you could also interpret, right, because here I have some function of u times u, so you could also interpret this as basically a selection mechanism or a gating mechanism that has been used before in RNNs. So like if u of t, b of u goes to 0, that's basically it lets the model select or say, okay, these parts of my input I don't really care, so just don't even take them, just drop them now, and only keep the ones you care about. So of course that's not the whole story. So because now it's time varying, you cannot use convolutions as you had before. Um, but remember, right, this phi matrix that we saw at the beginning is simply a product of matrices. And because matrix product is associative, um, typically associative operations, the nice thing is that you can like split them in any order, and so that's really nice if you're trying to do that in parallel, because I could split this product into different parts and compute it easily in parallel. And so that's the key, the rough intuition, at least for the coup de black magic that they use in Mamba to make this work, is that because you can still compute this in not as a convolution, but you can still compute it in parallel, specifically a parallel scan, and then doing some very clever and probably evil coup de magic to make that efficient. They're able to have a model that scales faster than transformers, at least for the sizes that they tested, and does like get closer to transformers in terms of what they can achieve in modeling. Okay, so now is the time for the Galaxy Brain take. So I'm going to claim and try to explain that basically Mamba is a bit like a Turing machine. Hopefully you guys survive. Hopefully my explanation is not completely incoherent, but probably I should start by explaining what a Turing machine even is. So a Turing machine, at least in like the original sense, is that you have this idea of an infinite tape, and on the tape has slots on which you can write symbols, and you have like a finite set of symbols that you can write on it. And then you have a machine that looks at a single slot on the tape, looks at the symbol, depending on the interleaved state of the machine, which is also finite, writes a new symbol on the tape, goes to a new state, and then shifts the tape left or right. And so you can sort of make a comparison between this and state models, like let's say my tape here, uh, making an abstraction over the fact that the symbols are finite. This is sort of like the input, right? I have a sequence of symbols or a sequence of values that is my input, and then I modify them based on my internal state and then write a new one. So in some sense, you could say that the Turing machine if you, sort of takes an input, as input the input tape, does some stuff, and then when it's done, it's the output. So the machine itself is at a state in some finite set Q. I'm going to claim that this is basically the state in the state space models, and then how the Turing machine performs. It's all described in some kind of transition function delta that describes given the state, so x of t here or q, and the state of the tape where the machine is. It's going to output the new state of the machine, the new symbol on the tape, so what it should write, and then whether it should move to the left or right. So first of all, hopefully this might be the most disgusting slide I've made here, but anyway, um, you can actually like map this like symbols and finite symbols in Turing machine to actual vector spaces. So the trick here is that because I have a finite state of finite number of symbols, I can map them to just vectors in my vector space. And to be even more egregious, let's take basis vectors or one-hot vectors in like r to the q or r to the gamma. I can always do that, no problem. And so now my full state, it's the state of the machine, which is now a vector in RQ, and the infinite tape, so it's a sequence that goes to the infinite on the left and to the infinite on the right of vectors in R gamma. So that's this disgusting thing here. And now I can actually encode the operation of delta as a map that takes my current state and returns a linear operator that then depends on my state, and then I apply that linear operator to get the new state. Hopefully, this is not completely incoherent, but so the idea is that if I have my state at some time t is q and x, so q is the state of the machine, x is the whole tape, then it only depends on q and the state of the tape at the 0th position. And so I claim that you can actually do that as a function delta times this tensor product object. This is more technicality, but just remember it depends on both. As an example, so let's say I have a machine with states, so machine states A and B, and tape states 0 and 1. And let's imagine that my Turing machine, takes the state A0 and maps it to B, state B, writes 1 on the tape, and then moves right. So all of these, because now I have vectors, I can do that using simply, so not permutation, sorry, but at least linear operator. Because I just need a linear map that takes my basis vector E of A, so that corresponds to state A, to E of B, the vector that corresponds to state B. So that's a linear operator because for the rest it doesn't do anything. And I can do the same for the mapping of 0 to 1, not a problem. So, and I'll have two just linear operators, at least on RQ and R gamma, that simply just move basis vectors around. And then shifting the tape, that's also a linear operator. It's called the right shift, the shift operator, S1. So it takes the sequence, so from minus infinity, x minus 1, x0, x1, and it just shifts all the items to the right by 1. So now I can write my new operator dx, delta of x, that depends on q and x, as simply so on the state I just apply p of a to b, and then on the tape I first apply my map d from 0 to 1, and then I shift. And I claim that actually you could, if you have a Turing machine, it's just a bunch of transitions like this. You have a list for maybe all possible inputs. You could also do that for this whole step for every single input, and at the end you'd have a map delta x that produces a linear operator. So it's not quite linear, but it sort of looks like it. So the punchline is that if you look at linear systems, well, first of all, you only go in one direction. You cannot go back and write the previous input output. So you could say that linear systems basically are Turing machines, but that can only go to the left in this case. And that they have a special form, but close enough. So I claim that linear systems are Turing machines that can only go to the left, and they're built bilinear, so they depend on x and t and u of t. And then Mamba, right? Because the only difference between this on the above and Mamba on the bottom is just the dependence on x of t on the state, and so Mamba just only depends on the input. And so Mamba, in some sense, obviously I've sort of stretched it a bit. It's a Turing machine that only goes left, and whose transitions depends only on the tape. So that was my shitpost for the day. But if people want to discuss actual details in the paper, we can do that. Hello.
Thank you. That was very thorough.
So can I go over what part exactly?
Uh,
Oh, the Galaxy Brain take. So, sorry, Vedu, you wanted to say something?
yep. Did you meant to have B bar XT instead of UT, or is that X?
Um, it is so here B is supposed to depend on x of t and u of t.
No, not that. Below,
Below?
below where Mamba is a
So
Turing
that
machine.
yeah, that's supposed to be a plus. It does not look like a plus, but it is a plus. Sorry.
No, I meant, is that supposed to be XT, like B bar depending on XT, or is it just depending on UT and it's also
So
linear
here,
with respect to UT?
so here, remember that so it's B that depends on u of t, and then it's a matrix that's applied to u of t.
I see.
Yeah,
Okay.
it's not the easiest to write that, but yeah. So back to Jimmy's question, sorry. So the Galaxy Brain take, right, is that Mamba sort of looks like a Turing machine, but in a very convoluted sense. So yeah, obviously I sort of skipped over the fact that Mamba does not have an infinite tape, but that's sort of something you could like you could assume that you have a Turing machine that sort of only goes through finite steps. But yeah, obviously there's the infinite memory part. I sort of look at also at this. You can also like frame maybe transformers as something like this. But
Now, do they use Hippo for initialization of A?
in Mamba, yes. At least they mentioned that they use the Hippo matrix. Oops. I think in Mamba they mentioned that they use this matrix here.
And this is from the Hippo paper, right?
This one is from the Mamba paper.
Oh,
Whoops, wait. If I can look.
yeah, because I'm looking it up right now. It says that you can also use some other initialization.
Yeah,
It should work fine, but I think they use Hippo. It's not clearly mentioned.
I think no, I think they mentioned in the beginning of the Mamba paper that they used a specific matrix.
Okay. Sounds good.
Um, at least I'm sure I saw it here. But one thing that confused me, for example, if you look at this algorithm here, uh, it says that A does not depend on the input. So that's one thing that confused me because
Yep.
some other sources mention that A does depend on it, sometimes it doesn't. But they do mention in the ablations that the most important parameter is this L delta. So controlling the step size is really the most important. And also interesting,
I feel like it should not depend on input because they keep it in the GPU part. If you go where they talk about cache, like GPU cache and the bigger memory, I don't remember the words technically, but
in
they keep A
SOA it
matrix
does.
in the fast access. So it has to
Yeah,
not depend on input. It has to remain
yeah,
same.
I think probably in this they mean that A does not change.
Yep.
My mouse is a bit crappy today. I'm sure I saw in
If you go
here
to the
that
kernel
they
part,
mentioned the Hippo matrix. Actually, they do mention. So initialization, they use the so yeah, based on the Hippo theory, an filament of A as this thing here, which I think looks like the Legendre matrix. Okay, I guess they had not mentioned it. Yeah, I guess I confused between that and the S4 paper. I think the S4 paper does specifically use the that matrix here,
yeah.
and they use that for the initialization for Mamba.
Yep, it definitely does. I think in this they are ambiguous, but it seems like they use it, but they say that you don't need to use it for Mamba.
Yeah,
Yeah,
but I think
because I was reading the annotated S4 blog, and in there the Hippo matrix was used, so I could tell that yeah, at least in S4 definitely they use it.
I think um, I think somewhere in there they were doing some ablations on the yeah they were looking at ablations for the which important parameters. They were saying the delta is the most important, and I think they also look at the yeah which parts were important. So specifically they were mentioning the initialization where taking the hippo initialization of a random one works differently. That's more details. Yeah, so if someone knows exactly which part is where it is, that would be grand. Nope. Of course, I don't know where it is. Maybe here. Model ablation is perfect. So yeah, they mentioned that the most important is the delta. Yeah, there we go. So architecture. And yeah, they look at the initialization here for different things. So they mentioned that this, but then again here they mentioned A of n, which does not make sense if A is a matrix. I'm now very confused. Okay. Yeah. Anyway, they do look at the initialization, and I'm very sure they use the Hippo one, but that depends on where you read it from. If A changed, I wonder if there's a projection type and a parameterization for dynamic A that can let you compute shifts efficiently. Um, I mean, in principle, the shift it still applies that you can compute the shift, but I think what you might lose is the coup de dark magic that lets things work. So because obviously, like okay, in principle they have something that depends on input, but really the arguably the main trick is that is this whole like low level CUDA stuff that lets it be efficient. Okay, are there any more questions? I see nothing in the thread or in the chat. So I guess no more questions. So we can wrap it up. Oh, maybe one more question. So storing history in Legendre Police. Yeah. Um, hopefully my explanation of the whole polynomial thing was okay.
Yeah, basically we are using a sequence of orthogonal polynomials to approximate the matrix, right? Or like function in simple case.
Yeah, that's basically that. But the way they do it is actually still fairly sophisticated, right? Because it's a sliding approximation where you discard some stuff and you update using an ODE. But But yeah, honestly, I liked like skimming and reading the Hippo paper because it was like, oh, this is beautiful mathematics. Um, but yeah, it's all basically it's all approximation theory with some twist.
I see. Nice, nice. I'm studying martingales right now, and I was proving a simple result
I
about like simple difference martingale being like being orthogonal, but like that's very different. It's just like a side thing.
Yeah, you mean so martingale stochastic process here, right?
Yep.
Yeah, cool. Yeah, that's a bit different. Although I think I've seen some references on state space models where you also have a noise term, but again, I think that's also different. But specifically for stochastic processes, there's some theorem that tell you that you can always express them as some kind of power, not power series, but find some basis of eigenfunctions of your covariance operator and your 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 stochastic sample is just some series in that basis. Okay, so no more questions. No more questions. Okay, so thanks everyone. Hopefully this was fun for you, at least as much as it was for me. So that sort of leaves what we'll be talking about next time. So I think we'll be talking about chaos. I'm not sure I can do that in 2 weeks because I do want to prepare it well. But it's also going to be a treat. So I'll keep you guys posted. And of course, if there's any other topics that people want to discuss, post it in the thread. Um, I'm also committing to some very special thing on the 1st of April because it's also a Sunday, so stay tuned for that. Anyway, so thanks everyone for coming. Hopefully you enjoyed it, and see you guys next time.